All right, so this recording is to provide additional supporting materials for students in selection of engineering materials for the eco related design and also the processes. Well, the learning objectives for basically this week is about first to understand the eco-informed design and also to get the concepts of material selection and processes. Yeah, we have been speaking about material selection quite a lot, but you have to know the materials in terms of their mechanical properties are not just the single item we consider when we do the selection, as you have to consider processes, as we discussed before. For many cases, we determine the bamboo as the best material in terms of stiffness, even strength. But in reality, you seldomly use that in many engineering structures. Yeah, by understanding processes, you will finally know what really the processes we can use to shape, join, and finally have a good surface of our final product. So processes are also a important chapter for us to always discuss and think of when you do the design. And after the knowledge and understanding, we hope you will be able to use the material indices in the eco selection. So this is a separate unit of the EduPack. And to do the eco-informed design, that's the first skill. And the second, you could also connect processes with the materials when you do generally material selection in any design processes. Yeah. And finally, we would like you to be able always use those skills and abilities and understandings in a bigger picture. You could always think about environmental related issues and impacts in terms of CO2 emission, in terms of energy use. It is becoming really a critical issue even nowadays. Yeah. I think everybody knows what is going on with the geopolitical issues. So that makes all this kind of concern about environmental impact and sustainability more important when you do any kind of designs. All right, in the resources, you have the textbook. Yeah. And in addition to that, so there are two books for you to also read if you're interested in this topic. Yeah, the first is the Materials Engineering Science Processing and Design by Ashby, and the second is all really very much dedicated to materials and environment, also by Professor Ashby. All right, so what is the outline of today's lecture? So before we go to the lecture, the outline, I would like to already show you two pictures, which is not directly related to kind of impact or environment or let's say energy use, but it's a slightly remote related. So I think these two pictures are good for us to get the introduction about the general let's say motivation of where we're doing right now in the energy sector exactly. So you can see on the first one on the left, I'm showing you one let's say a burnout of Tesla Model S. Yeah, the accident happened actually in 2018 in May. It happened in Switzerland. You can see the accident was pretty simple. The Tesla Model S basically had a crash on the barrier, this kind of steel made thing, and that really caused some very severe damage to the batteries, and that battery finally induced a thermal runaway and also in the end a big fire. So this is one very burning issues for electric vehicles. Yeah. So the safety issue is very, very big, important issue for them to consider in the use. So here on the right, I'm showing you one battery. Yeah, right here you can see this is a cell phone battery. Yeah, it's much a smaller one. And before this the battery was getting all this smoke and so on, if you just pay attention a little bit, you see there's a kind of needle. Yeah, it's bigger than a needle, but it's a very sharp tool with a little bit impact. You see that the height is really small. Yeah, it's within 1 meter even. And this little impact with this small machine, you can see cause really a significant damage to the battery and smoking here, and also thermal runaway. I mean, if it's more severe, you can imagine that will trigger some explosion or big fire like we have seen from this Tesla. So this is a little bit challenging for the electric vehicles, but what is the connection to our course? Yeah, I'm showing you really bad things about EVs, about batteries, but why we are still using them, why we are still promoting them so badly, in basically all the sectors. Yeah, and then I will show you a little bit about this. So this is the outline of today's lecture. So first, we will show you the strategy about eco-informed selection. And before the strategy, I will also tell you why we need to basically consider the energy use, consider the CO2 emission so importantly, and to promote all the use of this EVs, even though they could have really significant kind of dangerous events. And after that, we'll go to a case study, and it's about drinking containers. Yeah, it's a very interesting one. And finally, I will talk a little bit about processes, but that will be rather short. I think you can get the sense pretty easily from the book. All right, let's move to the first concept. So, and this is about this EU strategy vision about net zero of CO2 emission by 2050. Yeah, I think most of you have heard this 1.5 degrees C scenarios. Yeah, and if you don't know, I could explain just shortly. You know, this is a scenario we kind of, I guess, more than 200 nations agreed during this Paris Agreement in 2015. And the detailed agreement is, it says we cannot exceed a 1.5 degrees C global warming by 2050. Yeah, otherwise, we will really enter very serious problems. Yeah, so this simply is called Paris Agreement, and or also called 1.5 C and 1.5 degrees C scenarios. Yeah, so this is the name of it and what it means in general. And basically, this requires us to reduce the CO2 emission. You know, the global warming is mainly caused by greenhouse gases, and CO2 is the major issue of there. And so just to meet this kind of strategy vision, yeah, or this kind of requirements, EU made the following basically strategy here. So if you look at the current emission of CO2, and now we have in Europe, now we have an annual CO2 emission. If you just take a look at 2020, because this is actual data, we're close to basically 4,000 million tons per year. Yeah, so 4,000 million tons is quite a lot. And if we want to get this Paris Agreement realistic, yeah, we have to reduce it significantly, because the increase of the global warming, everybody has seen, is dramatic in the past years. And we want to reduce it to a final situation, which is so-called net zero. So net zero means the plus and minus of CO2 will be zero. So plants can take CO2 and make them negative. But we also want to encourage other technologies basically to observe CO2 and give something else. Yeah. So That's why net zero doesn't mean we do not emit CO2 at all. Means we emit CO2 in an equal amount as the amount we could handle just to observe. So this will be net zero by 2050. And you see, this is now, and this is 2050. So the task is very, very hard. Yeah, if you just pay a little bit more attention, the very big contributors to the CO2 emission actually are these three guys. Yeah, you see, this is transport, and the light blue is industry, so general industry, like PowerPoint and steel making, all this industry. And sorry, the dark blue will be really power plant and power related CO2 emission. That's a big issue for us to get energy and also to burn, to emit CO2. So these three are critically related to the CO2 emission. If we just look at a little bit more detailed sector, which is the transport sector, and here I'm trying to explain you why we need to go with the EVs. Yeah. So finally, to let you know why we have to do that. So this is a diagram, rather complicated, but if you just look at it, so here's now, or a little bit earlier than now. And this is our CO2 emission basically for transport only. Now, you see this is around about 500 million ton CO2 per year. And that's quite already a big fraction, as we see from last diagram. And now if we want to reduce it, so you see we have different scenarios. You don't need to look at all of them. It's really a very detailed analysis. The reference means basically if we don't do anything, we just let it run. We don't enforce any kind of policies or technologies especially related to, let's say, CO2 control or energy and sustainable energy use. And this is what we will get. We will generally get a little bit less CO2 emission, but this is far beyond the zero emissions still, right? And if you work a little bit harder in between, like the other scenarios like this, we can get it better. But if we want to meet the Paris Agreement, so the 1.5 degree C, we actually need to follow this green. So this green, this is our goal to basically reduce all this 600 million ton CO2. And what is the reaction? So the reaction basically is this two. We need to increase a lot share of the public transportation use. So at the moment we have around about 12%, and we need to get 34%. I think this is really getting pretty good, especially in Nordic countries. Public transportation is getting very much in a big share. And the second measure is more critical, because we have to also consider, the urban fleet, so basically cars and buses. And if you want to meet the Paris Agreement, meaning we will have to go with electric vehicles. It doesn't mean always electric battery or lithium-ion battery driven. It could be also other kind of fuel cells and so on. But the bottom line is the vehicles cannot use fossil fuels. That will generate CO2. And this has to go 100%. So you can imagine in about 30 years in the kind of urban fleet, you will not see any cars running by diesel or gasoline. So this is something we have to imagine right now, otherwise we'll have big trouble with the climate. And this is also the fundamental reason why we have to go with electric batteries in the vehicles, or in general, just electric driven vehicles. All right. Now it comes to the design phase. So I think that was a good motivation for you, maybe some additional information for you to realize why we're really promoting kind of green energy and also green use of energy in different industries. And here I'm showing you a diagram just to consider when you really go to the material selection field, when you go to the, let's say, the product design field, what is a life cycle of material we should consider. Yeah, and the basic information is we have material production and we also have the product, let's say, manufacturing. So the cycle goes from here. So we take the natural resources. Yeah, if we think about aluminum alloys or steels, you will take the ores from the earth, basically. Yeah. Then you go through already a long process, iron making, steel making, and cold rolling, heat treatment, and all these processes. You basically get your raw materials, yeah, in terms of sheet, in terms of wire. And if you want to produce, let's say, a car, yeah, the body of the car, then you need to go through the product manufacturing procedure, basically by stamping, by all the different kinds of shaping, and then you finally get the body of your car. And then you get your car and you're going to use the product. Let's say you're going to use the product for 10 years, 20 years. And then the product is not in a very good shape. That is determined as the end of the life, but you have to pay attention, it's the end of the first life. Yeah. So after the end of first life, some of the products, yeah, will basically go into this two fields. So the first is combustion. You see, most likely for our plastic kind of garbage and so on. Yeah, they might have to go to such a phase. And if you think about nuclear related kind of waste and so on, they will have to go with landfills because we basically have to end their life right now. But for others, and we would like to promote the most of the others, go to this three kind of directions. So after the end of the first line, we want to give their second line, basically. So they can be recycled or downcycled, yeah, unless you deal with lots of, let's say, the can of Coca-Cola and all the others. So they will be recycled, basically, yeah, to the material production again. So you will use them to reproduce some steel, aluminum alloys, things like this. And you could also get a basically upgrade on refurbishment, for example, for a second-hand car. Yeah, you could do that. Or you can basically to reuse it. Yeah. So directly use it, yeah, for the first after the end of first life. So these are the three directions we would like to think, which are doing positive things. Yeah. If you just look at all these orange colored arrows, they're consuming energy. They're consuming energy. They're emitting CO2 most likely. And after the end of the first life, okay, we're not even here. We're probably still consuming energy and also emitting CO2. Yeah, they should have the orange as well, actually. But these three green arrows, and they're doing good things. So they're not consuming energy because they are contributing positively to our material use and to our CO2 emission. So these are the things we should promote and we should think when we do the design. So basically, this is the so-called material life cycle, and you could have in mind. And why it's important, because the kind of equal impact that our product and on the material will make will be decided already 80% during the design stage. So when you design your product, when you do the material selection at this phase, at the design phase, Yeah, you choose the material, you choose the processes, and you choose the use, and you probably already maybe not choose, but by all your choices, the end of the first life choices are also made. Now, that's why it's critical when you do the design, you need to consider this whole picture. And 80% of the eco impact is already determined during the design phase. Yeah. So that's why we need to have a tool basically to estimate what is the eco impact, yeah, in terms of energy use, in terms of CO2 emission. And this will give you certain information about the eco impact, and that will also basically decide how you do your material selection afterwards. Yeah. So this is basically the strategy we're gonna do, and why we need to have the eco-informed design principle in the material selection. And as you can see, the other kind of instruments like government promoted CO2 footprint tracker, and also legislation about CO2 or carbon taxes and so on. So basically they're all forcing everybody to consider the eco impact, and this has to be considered during the design of your product. And in the next, I'm going to show you how this strategy, when you consider the CO2 emission in the design phase. And basically it follows the following steps. You could get this from the book in more detail. Here I'm giving you a very rough, let's say, introduction about it. And there are a few steps first already. So we need a tool, as I said, and the tool is called Fast Eco Audit. Now this is included in the Greta pack. And you're going to use this to analyze the results and identify certain priorities. And then you explore basically different options of your material selection. And say, if we use another one or this one, can we get a better CO2, eco impact? And to visualize this here is what you see. Yeah. So this is the so-called energy that you're going to use in a material life. Yeah. So it's kind of a integrated measure of the impact to the eco impact. So the CO2 is part of it as well. And as you can see, we will see all the phases as we discussed before in the last slide into this material life cycle, basically. So you cannot just think about the material production. Now, this is the material production. So, for example, if here's steel, here's aluminum, yeah, and maybe you know, in the production of steel, it is a little bit larger scale, maybe more expensive, contains more energy, not more expensive when you do the material production. But you cannot only think about the material production. Yeah, you have to think all the following features, like manufacturing processes and transport and the product use and disposal. And this is end of life credit. As I said, the end of life credit will be inactive. So it will make your energy consumption in general lower. Yeah. So that's why if we can identify materials which could contribute a lot of end of life credit by reuse, by recycle, this is always very much encouraged. Yeah. And after that, you can just explore, as we discussed here, this two material, you can go basically more. Yeah, if we use another one, is it better? Can it be more systematic? And then you can just apply the selection methodology to finally then select the new material and processes, and then do the recommendation of the action and assess the potential savings between a bunch of materials you would like to think about. All right, so that was the general strategy. I think that was easy to follow. You can also get more details from the book. Now I'd like to give you one example, which is a quite interesting one, rather easy, but it really integrates many concepts we have learned in a few weeks ago, and also to think about this eco audit and or eco-impact design. So the example is about the eco selection for a fizzy drinking bottle. So looking like this, yeah. So it's not just a normal bottle. So there's will be there. This is the bubble water, yeah. So the water with gas. That gives a certain requirements of, let's say, strength requirements of the materials you will see in the following. And now we want to think about how can we do a eco selection, so the eco-friendly selection. So that means we need to minimize the embodied energy. Yeah, that's the thing we want to consider. And you know how to do it, right? The design brief is like improve green credentials of the bottle. We want to improve the embodied energy. Then we can basically translate it to constraints and objectives. So the constraints for such a bottle design is basically it should be able to be molded and it's transparent or translucent. You want to see what is inside, what is the color of, if it's just water or cola. And one of that, it should be able to contain pressure. Yeah, that's we want to have the water with gas. And objective is simple, so we want to be more eco-friendly. We want to minimize the embodied energy of the bottle. Basically using the eco-audit tool. So here is a little bit about this calculation, because we have one constraint which is about to contain certain pressure, and you should know the pressure and how this pressure will be related to our material requirements, right? So here I'm giving you all the abbreviations of the symbols, and you can see the pressure, by very simple mechanics. The pressure can be basically expressed like P, the pressure here, and times R. So R is the radius of the bottle divided by T, the thickness. And this will be the strength, the circumstantial strength of the bottle. And of course, if we would like to the material to contain certain pressure, means this strength of the material has to be smaller than the yield strength, right? Otherwise, the material will be having plastic deformation that will be already considered as failure of the bottle. Yeah. All right. Then we want to calculate the embodied energy of the bottle, right? So we don't want to get the whole bottle. We just want to get the embodied energy per unit area of the wall, right? Because we don't want to change the geometry of the material. We just need to know how can we minimize the embodied energy per unit area that you're already automatically minimizing the embedded energy of the bottle. So this is a simple equation. So you just, the energy is equal to the thickness times the HM is this embodied energy of material per kilo, and times the density rho, and then you get basically the embodied energy per unit area, right? I think everybody could follow. And the next is basically you take the T, right? We don't want to have any geometry in this kind of material index formulation. And we take the T from this first equation and replace the T by sigma Y, P, and R. And as you can see, here is our embodied energy. So if you want to minimize embodied energy, as you know, P and R, they're determined value. So that means we're basically minimizing this term here, the whole term. Now you can recall how do we formulate the material index, and we just take a reverse because we don't like minimization. We want to maximize. So we want to maximize sigma Y over HM times rho, right? So then you can just simply use our tool as learned in this first task to formulate a material index. Yeah, if we just go fast here, you can see we can express our material index in this kind of RGB diagram. Yeah, you take the x-axis as embodied energy times density, and the y-axis is the yield strength. Yeah. And then we're basically looking for a maximum accept here. So you can see here the best material for this minimized embodied energy is PLA. So PLA is a certain bipolymer material, and so this green one's TPS also, and you can imagine that's why they're here, because they're really, let's say, environmental friendly, and it can really get the minimized embodied energy. But if you know this material, and if you know this business also in detail, actually for our bottles used nowadays, we don't use this PLA so often. If you just take a look at your Coca-Cola bottle or any water bottle, maybe you can think that you can take a guess. They are mainly made of PET. Yeah, and you might ask, why is that? If we just recall the design principle. So here I said, okay, we just want to do a best eco-friendly selection. That's why we just want to minimize the embodied energy. But the truth is, in reality, you cannot only go for that, right? You can imagine we have to also think about the cost. You need to also always minimize the material cost. That has been really a fundamental driving force for many businesses. If you just add this into consideration, as you can see, I think we don't need to derive for the cost situation. Yeah, you can basically memorize the material index for cost related issues. And here, as we're looking for the yield strength, basically we just replaced HM by CM, which is the material cost per kilogram. Yeah. And that's your second, basically, material index. Now we have two material index, and you can easily think about how to solve this issue. So what we need to do is basically to construct a trade-off function, right? And then you will need to plot this, and then you can further basically go with the penalty function and make a detailed selection. Yeah, so here I'm showing you everything here with this now about the cost situation only. Yeah, so here we see if we just take the x-axis as price times density, yeah, as the cost only, and the y-axis as yield strength, you will now find the PET. So PET is right here. That's why we, in the reality, at the moment at least, most of these bottles are made of PET. And now, if we take consideration about costs and also the eco impact altogether, we can construct such a trade-off plot. So here is basically the price over yield strength, and here is the embodied energy over yield strength. And you can see this is our trade-off curve or trade-off front. Yeah. And so here is PET. So you can see here, and here's PLA. Yeah, exactly. They're on the front. If we don't consider price, we will definitely take PLA. And if we take more serious about price, less about the environmental impact, of course, PET is pretty good choice. Yeah. So far, as you can imagine, we're more taking the price into consideration. But now with all this government influence and also kind of good policies for using environmental friendly materials and so on, I could imagine we will more and more go towards such a direction. So if you formulate a penalty function, you can imagine the alpha value will be significantly influenced by that. That will make finally decide you will go a penalty function like this, or you will go with like that. That will decide based on different materials. All right, I think that's the example I would like to talk to you. Yeah, and you will learn much more from the book, and also from your task. You will also get a feeling about the use of audit. And the last thing I want to talk about is these processes. And here I'm showing you one diagram we have, I think, showed probably at the beginning of the course, maybe the first or second course. So this is the structure, yeah, of information. What we should do when you do the material selection, and what the EduPack is organized to let us use. Yeah, we focus a lot about the material database, and we were basically doing so many things in the past few weeks, right here. Yeah, you will also learn all the different materials, yeah, from metal alloys to hybrid. And today we're going to talk a little bit about the processes. Yeah, so as you can see here, and the processes data table is organized very similar to the materials data table, and you will see all these different kind of tree information in the next slide. Here basically I'm showing you three big families of processes. Yeah, so similar as materials, there are also three very important families. So we have joining here first, but maybe you can think about the shaping first, because you want to produce something like, for example, the car body. You will first try to get the shape of your, for example, the front panel, the bumper, and also the door panel, and all these parts. We need to first shape them. So there are many shaping methods like casting we have learned, and the material forming by stamping, by deep drawing, and all these processes are used as shaping methods. Yeah, and joining is next. So after you get all this, let's say door panel and the front panel and also bumpers, we need to put them into one piece, into the car basically. Then you need all the joining technologies. Yeah, maybe you can recall we had a very detailed look at especially welding, but also other joining methods during our seminar course. And finally, it's about surface treatment. Yeah, after you get the shape build and the piece joined together, when you consider how we're going to do the painting of your car, should you do some polishing, or you need to make the surface more rough? And these are all the surface related treatment. So after surface treatment, basically your product is done. Now what we need to do is do the selection of the processes. Yeah, so you're going to use this way of shaping or the other way, so casting or deep drawing or stamping. For joining, so this kind of laser welding or friction steel welding, and this will be the things you need to select. Of course, the most important thing is you need to select the links. So if the materials you select to fulfill the property requirements can be linked with the properties, with the processes you would like to shape, join, and surface trim. So this is also a very important key selection you need to do. So you have to make sure they're compatible with each other. All right, so here I'm showing you this organized information about processes. As we just discussed in the previous slide, they are also organized similar to the material tree. So this is so-called process tree. We have the family, these three big families, and then when you go to classes, for shaping, as you can see, molding, casting, deformation, and so on. And if you go more detailed about molding, you will see injection, flow and rotation and compression. Yeah, and if you go to injection in more detail, you will see the specific process attributes about injection and molding. Yeah, what kind of materials this could work with, what kind of shape this molding could produce, and size range, minimal selection, and so on. And you have this, let's say, numeric structured information, and also documentation with unstructured information, exactly as we learned from the material tree. Yeah. So I will not talk about all this in detail. And I think this is all. And for the process and eco impacts.